This is Dr. Holt. This video is on torque and angular acceleration where a block and wedge is present. This is a really good problem. I want to go over this one in somewhat detail. What we have here, we have a block of mass 3 kilograms and one of mass 8 kilograms are connected with a massless string over a pulley that is the shape of a disc that has a radius of 0.14 meters and has a mass of 9 kilograms. In addition, the blocks are allowed to move on a fixed block wedge of angle 30 degrees as shown. The coefficient of kinetic friction is 0.27. What we're going to do here, we're going to find the acceleration of the blocks and the tension in the massless spring. Alright, to do a problem like this, we're going to make the assumption that the system is going to move to the right, basically because you have a lot larger mass here. So to set up this problem, the first thing you want to do is draw yourself some good free body diagrams. We're going to draw one of the 3 to start out with. So I'll just draw a little dot, and I'll get some vectors here. Alright, we will have label all the vectors here. We'll have a vector coming up. So this one coming down. Since we have friction, we have this one going this way. We'll have our tension going this way. And then we'll have mass times acceleration going this way. Alright, I'll make that a little bit better. Maybe. Okay, there we go. So now let's go ahead and put in the values. This is 3 kilograms. So we're going to multiply 3 times 9.8. That's going to give us 29.4 newtons coming down. This is going to be our normal force up here, pointing back up. And obviously that would be 29.4 newtons also. Now all we have to do to find this frictional force is take 29.4. We're going to multiply it by the coefficient of friction of 0.27. When we do that, that will give us a frictional force of 7.938. Okay? We're going to label this vector here as our tension 1, being that this one here is going to be T1. And then this value here is going to be the mass times acceleration going to the right. Okay, so that's our first free body diagram. This is a free body diagram of the 3 kilogram object. Now let's draw another one over here. Alright, now before we do that, I want to break the 8 times 9.8 into components. So let's just talk about what we would do with that. What's occurring is you got 8 times 9.8 coming down. You're going to have a normal vector coming back in this way, and you're going to have this vector coming back in this way. So the components are going to be going normal to the surface, and one's going to be going parallel to the surface. Now, if this is 30 degrees here, this angle right here would be 60 degrees, and this angle right here would be 30 degrees. So we know that this force here is going to be 8 times 9.8 times the cosine of 30. This one here we could say is going to be 8 times 9.8 times the cosine of 60, or 8 times 9.8 times the sine of 30. Either one's going to be fine. So we'll go ahead and draw our free body diagram now using only the components. I'm not going to use the 8 times 9.8. Alright, go ahead and do that. What I'll get would be I'll have a vector coming down here. I'll have the tension going back up this way. I will have friction going back up this way. I will also have mass times acceleration going back down this way. I will have the normal force of the this wedge here pushing back up, and I'll have this one coming back down this way. Okay, we'll go ahead and put values that we know. Okay, so if we take 8 times 9.8 times the cosine of 30, that's going to give me a value here of 67.89. That means my normal force, Fn, would also equal to 67.89. Okay, now I need to find out what my frictional force is going to be. My frictional force is going to be my normal force times 0.27. So 67.89 times 0.27 is going to give me a frictional force of 18.33. Okay, and then I'm going to take 8 times 9.8 times the cosine of 60. That's going to give me this force going down, the parallel force. That's going to give me a value of 39.2. This is going to be my mass times acceleration, so we're going to write that as 8 times A. And we're going to label this as the tension as T2. This being T2 here. Okay. This free body diagram is a little bit more complex than what we did here, but again, it's a good free body diagram. I have everything labeled. Now what we want to do is see if we can come up with an equation here. I'm going to let everything that goes horizontal be my x, so I'm going to sum my forces in the x direction, and all I'm going to do is set that equal to mass times acceleration. Let's scroll down a little bit. So when I do that, I'm going to let anything that goes to the left be negative. That's going to give me negative 7.938 plus T1, and I'm going to set that equal to 3A. Okay, so now we're going to solve for T1 here, and I can say that T1 is going to equal to 3 times my acceleration plus 7.938. So we're going to hang on to that right there. Okay, we're going to do the same thing here. We're going to sum the forces. Now I'm going to let anything that comes down this way, I'm going to let be x prime. And again, you can label this anything you want. So now I'm going to sum the forces in the x prime direction, and I'm going to let anything that goes down, or anything that goes to the right, I'm going to let that be positive, and anything that goes up, I'm going to let that be negative, just to be consistent with what I did here. Alright, so when I do that, I'm going to get a, again, I'm going to set that equal to mass times acceleration. Sorry about that. So now let's put them in. I'm going to get a minus T2 minus 18.33. Make that 18 a little bit better so we can see that. Okay, plus 39, make that better too, 39.2 must equal to 8 times my acceleration. Again, summation of forces equal to mass times acceleration. What you want to do here is solve for T2. And when you do, you'll get T2 is equal to 20.87 minus 8 times acceleration. Okay, so we're slowly working through this. So now we know what T1 is and T2. We don't know the numerical values, but we have them in terms of acceleration. Okay, what I want to do now is I want to draw myself a free body diagram of what's taking place on the pulley itself. So if I draw a free body diagram of the pulley, obviously it has mass. So I'm going to have a vector coming down here, and I'm going to have the normal going back up, and now I'm going to just draw like a little picture of kind of what the pulley is going to look like. Something like that. Now we know the pulley has a mass of 8, so we'll multiply that by 8. Let me go back. Was it 8 or 9 real quick? Sorry. Actually it's 9. Let me change that. Pulley has a mass of 9, so this would be 9 times 9.8. Now this isn't going to matter, and this would be the normal force pushing back up, and again that is going to be 9 times 9.8. Okay, again that values I really don't care on this problem. What I care about is getting the tension directions right. Now what you want to do here is, since the tension here is going to the right, at the pulley you want to make it go back to the opposite direction. So I got tension going this way, and I got tension going this way, like this. So I label this as T1, and I label this as T2. Now, according to the cross product, that torque is always going to equal to the the radius, the distance the force is away from the center point, we'll make it a vector, cross product into the force. Okay, now if you use right hand rule, that means that anything that goes this way is going to be positive, and anything that goes this way is going to be negative. Okay, and I'm going to follow that sign convention here. I just think it makes things easier. So what I can say here is there's a couple things we know when we talk about torque. We know that torque, the summation of torque, is always equal to the moment of inertia times the angular acceleration. So we're going to go back here, we're going to do the computation on torque. Now we need to go find what the radius was of that pulley. The radius of the pulley is 0.14. So I can say that T1 times 0.14, now I'm going to do minus because this is going to make it want to go clockwise, T2, okay? Now, here's what you're going to be careful with. Since I'm using this sign convention of anything that goes to the right or goes clockwise as being negative, I'm going to make my acceleration be negative too. And again, that's just for consistency. Alright, so now we can solve this problem. We know a couple things. We know that acceleration is equal to angular acceleration times r. So can we not say that acceleration is going to equal to my angular acceleration times the radius, which is 0.14? So we can say angular acceleration is equal to acceleration over 0.14. Alright, so we're going to rewrite this again. Let's scroll down a little bit to give myself some more room here. So I can say that T1 times 0.14 minus T2 times 0.14 is equal to I times acceleration over 0.14. Now what we want to do now is go find what the moment of inertia is going to be, and we know the moment of inertia for an object that is like this is going to be 1/2 times the mass times radius squared. So we'll run that number. So I, the moment of inertia, is going to equal to 1/2 times the mass, which we know is going to be 9, times 0.14 being the radius squared. So let's redo that, and that's going to give us 1/2 times 9 is going to give me 4.5 times 0.14 squared times my acceleration over 0.14 is equal to T1 times 0.14 minus T2 times 0.14. Alright, let's see if we can start simplifying some things here. We can cancel out this, and we can cancel out this. When we do that, that means I can cancel out these radiuses also. Now I got a pretty simple equation. And now you only need to be careful with is, since I made this negative, I almost missed that. Since I made this negative here is going to carry over here and here. So please make sure you do that, because otherwise you're definitely going to get the wrong answer. So now we're going to do T1 minus T2 must equal to a minus 4.5 times acceleration. Alright, now we know previously we have these values here. Let's grab those values. So if I can grab that and drag it down, I'll copy that. Bring that down to here. We know that. Let's go back up and get the other one. Alright, we do these values. So now all we have to do is put these in, and we should be able to solve this problem. Alright, T1, we have 3 times acceleration plus 7.938 minus this, so make sure you distribute the negative, 20.87 plus 8 times acceleration is equal to negative 4.5 times acceleration. I'm going to add these up, the acceleration, that gives me 11. Bring this over to the other side. That's going to give me 15.5 times my acceleration is equal to, I'm going to add these two numbers here together, bring those over to the other side, and let me just run that real quick and see what I'm going to get. Actually, that gives me 12.932. I got that written down. 12.932. Divide both sides by 15.5 and you're going to get your acceleration is going to be 0.834 meters per second squared. Alright, so now we have the acceleration, and now the whole problem just falls apart because all I have to do is take this acceleration, put it into here, calculate what T1 is going to be, and when I do that I will get T1 is equal to 10.44 newtons. Take the acceleration, put it back into here, you will get T2 is equal to 14.198 newtons. And that's the solution to the problem. Again, the problem looks difficult. It's not too bad. The key to all this, again, is consistency in drawing good free body diagrams. Draw good free body diagrams, label what T1 is going to be. Do the same thing over here, label what T2 is going to be. Then just come down, draw yourself another free body diagram of the pulley itself, and make sure that you have the T1s and T2s going the opposite direction as what they were at the other masses. Then go back knowing that the summation of torques is going to be equal to the moment of inertia times angular acceleration. Substitute angular acceleration in terms of A, and then the whole problem just kind of falls apart. Alright, best of luck with this. I hope this video helped you solve a block and a wedge.